Hey, let's take a look at a photoelectric effect experiment question. So in this question, I have a stem here from which we can probably go a number of different ways, and I'll demonstrate a couple of basic questions and maybe a more advanced one that can be asked based on this scenario. So in this question, they describe an experiment takes place. Light with a wavelength of 350 nanometers hits a metal surface and produces a current of 3.50 amperes. Then experimenter must apply a voltage of 1.90 volts to reduce the current to zero. So we got some quantitative information there. Let's take a look at the question. What is the work function of the metal? So if you understand the experiment, they're describing kind of the classic setup, and that is situation where some incoming photon with energy EP, energy of the photon, is equal to two things. The photon energy gets converted into, firstly, the work function, given the symbol W, and then any leftover energy turns into the kinetic energy of the emitted photoelectron. So pretty fairly straightforward start to this question, and pretty typical as well. What you then want to do is start teasing out the formulas where it's necessary. If we don't know the photon energy, then we want to write down the formula, hc over lambda in this case, to calculate the photon energy. Work function we do not know, but we're going to try and solve for. And then the kinetic energy, there's two ways to view kinetic energy in this experiment. On the one hand, the kinetic energy could be 1/2 mv squared. That's kind of our classic kinetic energy of any massive particle with speed, and this will have that. On the other hand, in the experiment, the other formula we have is that the kinetic energy was found using the stopping voltage and would be equal to kV stop. So in this case, we have the stopping voltage, so I'm going to choose to use that form or that version of the kinetic energy for the photoelectron that's emitted. So as you can see at this point, I have really all values in here that I either know or that are given to me in the question, except for the only unknown at this point right now is the W. So we can either rearrange and then solve for W, or we could go ahead and do some calculations. I think I'll start plugging in some variables right now. Big question to ask yourself at this point before we go on is, are we going to work in joules, or do you want to work in electron volts? And usually you kind of roll with whatever the question gives you. In this case, doesn't look like there's really a preference or a slant to this question saying, well, find it out in joules. There's no information given in joules or electron volts, so it looks like we have the choice here. Given the choice, my personal preference is to use the electron volts version of Planck's constant, only because you end up with numbers that are a little easier to work with. So H in terms of electron volts is 4.14. So 4.14 times 10 to the minus 15 joules times seconds, multiplied by 3 times 10 to the 8th for the speed of light, c, meters per second, divided by the wavelength given in the question is 350 nanometers, so that's 10 to the minus 9 meters. That should be equal to the work function, first of all, plus Q charge. Now, because I'm working in electron volts, my charge is just going to be the charge equivalent of 1 electron multiplied by 1.90 volts. So you can start to see how this gets a little easier to wrap your brain around. We'll have W plus, on this side, 1.90 electron volts worth of energy. And on the other side, we'll get our energy of the incoming photon in electron volts, 4.14 times 10 to the minus 15 times 3 times 10 to the 8th divided by 350 times 10 to the minus 9. I get 3.5 over here, 3.55 approximately electron volts. So here's a real stripped down version of what happened then. We had an incoming photon with 3.55 electron volts worth of energy being annihilated or losing all of its energy, and it's being converted into work function plus 1.90 electron volts worth of kinetic energy. And so in the end, I think it's easy to see, or the mathematics that remains is pretty straightforward. Of the 3.55 electron volts, subtract 1.90 because that turned into kinetic energy, then the work function was 1.65 electron volts worth of work function. So that is my answer.